Okay, I think we can start. Today, again, Luca will cover black box attacks and then a part on malicious executable files, how to manipulate them to evade detection of machine learning algorithms. And tomorrow, I will present a part on defenses, on how to counter evasion attacks and adversarial examples. And then we will start poisoning attacks, which are, again, a different kind of attacks that we can have on machine learning models, as we discussed yesterday. Okay, if there are no pressing questions or other issues from you, I think we can start. So I can leave the floor to Luca, and I'll stay connected for a while. Okay, thank you, Luca. Please go on.
Okay, thank you for the introduction. So again, if you have like a couple of questions before starting to deep dive into the world of gradient-free evasion attacks, I mean, you have the chance right now. Of course, you can ask them later on. Also, like, please also ping me during the lesson if you have like curiosity or whatsoever. I'll be very happy to answer. So okay, I think that this science means that we can start. So we left yesterday with the all world of gradient-based attacks. And just to recap a bit, you can compute the gradient, that is like the direction of maximum ascent, and then you can use it to guide the starting point of the attack toward the class that you want to reach. But the problem is that, gradients are nice and cool, and they're easy to compute, and there's like a lot of libraries that you can use for, use them and compute them. But the point is, not everything is gradient based. So today, in this first part of the lesson, we're going to cover what else rather than gradient attacks. So first of all, the motivation of this. So why we can't use gradients? Well, first thing is that the model the model under attack, your target, might be not differentiable. So imagine, for instance, a random forest classifier. You have just like binary decisions, like if A equals 10, go left, otherwise go right. If B is stricter than 0, go left, otherwise go right. This is clearly not differentiable. And of course, these incapacitate all of the gradient-based attack that I told you yesterday. You can't use a Carlini-Wagner attack on a random forest classifier. That's the very same thing for, like, you mean, like, let's say K nearest neighbor. You can say, like, okay, I compute like the gradient of that because it's just like the summation. It's a voting system. You can compute the gradient over that. So that's the very first reason. The second reason is that maybe the target of your attack is unavailable in the sense that you don't have the model. Because to compute a gradient, you have to physically have the model on your machine or on a device that provides you with that information. And if such information is not provided, well, you can't use Carlini-Wagner on that. So for instance, imagine all of these services that right now are available online that are so-called machine learning as a service, or the MLAAS. I think you already saw this term somewhere on the internet. And basically what this system does is that they offer you computational power through the usage of APIs. So you send them like an image of this cell phone, and they recognize it as a cell phone, but the answer is going to be just a label. You're not going to have maybe you're going to have some scores, like it's like the phone for the 50% of probability, and it's a cap for the 10% probability, and just going down with other classes. Or just like 1 or 0, like is a cell phone or not. And that is only queryable through APIs. So you do a remote request and then you wait for the result. And clearly there is no gradient information here. So what you can do? Well, you can move on to the world of optimizers that do not use gradients. So first of all, you might want to say, okay, what about if I love gradients. I just want to use them as much as I can. So there should be a way to doing this. So yes, the answer is yes, you might. And you can do what is called, the so-called black box transfer attack. So instead of attacking the real model, that's, I mean, your target that is hosted somewhere on the internet, you create a surrogate. What's a surrogate? Essentially, it's an approximation of your target. Imagine that you have basically, you know the data that has been used for training this model, or again, you have some similar data to the model, I mean, that have been used by the model that is your target. So what you can do is that you can train a model by yourself using this data and the answers of the target that still is reachable somehow, because otherwise you couldn't even, I mean, trying to break it. So what you can do is you take its answers, and then you can compute an approximation of its decision boundary. Or rather, if you even don't care about training stuff, you can, I mean, you can cross your fingers, open Google, and find and browse for a similar model that has been, like, you know, released online as a pre-trained, that you can use again for computing gradient-based attack. Because now you own the model again, so you don't have the problem of, I mean, you don't have the unavailability problem that I told you before. And you're again, you know, in a world where things are differentiable, because of course, if you're training the model by yourself, you're gonna try to, I mean, to simplify your work as much as you can. And in this case, simplifying the work means create models that are differentiable. And then what you can do, so you train your model, I mean, your surrogate model, and then you compute gradient descent on it. So you use Carlini-Wagner, DeepFull, FGSM, or DDN, FMN, whatever you like, and you create your adversarial examples. I mean, maybe you don't create only one, you create, like, I mean, a lot of them, and then you take all of them and you send them to the real model. And if you're lucky enough, some of them are gonna evade the target classifier as well. This is again because the decision bound, I mean, intuitionally speak, I mean, from an intuition point of view, the boundaries of the two classifier are somehow similar. So these surrogate models, I mean, of course, there is no, like, I mean, winning strategies of choosing like one surrogate against the other. It's just a matter of how you train them. And I mean, in the literature, what they did is that, I mean, in the first work is that, okay, let's just, so we don't know this thing. So we take like famous classifier, like I take logistic regression, I take SVM, I take decision trees and KNN, and just, you know, compute attacks against, I mean, every of them against anybody else, and I see what happens. And this heat map shows you basically what happens when you like you create an attack for, let's say, an SVM, and you transfer against, like, I mean, a KNN algorithm or a ensemble classifier model or something else. And you see that basically different classifier learns different decision boundaries that, so, I mean, allows the attacker to evade less or more like the target model. So the problem is, so how can I mean, how the attacker can glimpse or can have a grasp of what's happening behind the hood? How can the attacker know if the transfer attack will work or not? And do this transfer attack works? So that's a very interesting question. So here, I mean, here I'm showing you like a plot from like one paper that has been published at Usenix in 2019, where they basically are investigating exactly this question: how and do really transfer attacks work? So as you can see here, you have like, this is the target, the real target classifier. This is the real target classifier, and this is the surrogate. And basically, what you wish to do is you would have liked to create adversarial example that evade both of them. And of course, the attack that you use matters, because if you have like a minimum distance attack, you are basically you're trying to approach the boundary as much as you can. So as you can see here, the yellow dot is the minimum distance attack, and is arrived like here. It is near the boundary that has been used for has been used for optimize the attack. And of course, since it's a minimum distance attack, it might not work on the real classifier, because the boundary it's okay that are similar, but they are not the same. So you might end up close to the boundary that you're using to optimize attack, but there might be very far away with respect to the real boundary you want to attack. On the contrary, when you use maximum confidence attack, maybe you inject a lot of perturbation inside your sample, but the sample might be, the transfer might work more with respect to the minimum distance because it doesn't minimize the boundary. So it's just trying to enter as much as it can the class, the target class. And that's, in this case, what this paper says is exactly that. So maximum confidence attack might transfer better than minimum distance attack. And to give you, a glimpse about that, in this paper, they also try to compute some metrics that, allow the attacker to understand if and how things might work. So imagine, this basically, this T is basically telling you how much is hard or not to land a transfer attack. And this thing basically depends on two things. The first is the size of the gradients, because if you have a very, very strong signal, well, it's very likely that you have a direction to follow, and maybe this might this might point you to a region where there are adversarial examples. And also what you want to see is the alignment of the gradients of the target model and the surrogate model. Because if these two are very aligned, it means that they basically have somehow the same shape, and adversarial examples are common. So you find them in the same direction. Otherwise, if they're orthogonal, it means that the boundary that you have constructed and the real boundary, they are totally different. So, if you need more, if you're more interested in transfer attacks, I really recommend you reading this paper, because there are a lot of more intel, and you might, you might end up reading a lot of things, and also understanding a bit of more of mathematics that, we skip for now, because it's not that expensive, but there are some tricky things to take care of. So just to give you a brief recap about transfer attacks, we have a lot of benefits, because you don't need the original model. You can start you can start just with data and see what happens. Then also, depending on the domain, the data are already available online. Think about images of cat and dogs. You open Google and you can browse a lot of cats and dogs as much as you like. And also in other domain, spoiler, in malware, there are online repositories that you can browse and download as many malware as you want. So basically, most of the state-of-the-art classifier uses the same data sources. And this is not, from an attacker perspective, these are very good, because you already know which data you should use to train a surrogate. And also, transfer attack can also happen on model that, even if they are not trained on exactly same data, they solve a similar problem, because somehow the decision boundary might still be similar. And that's, again, for the attacker is a good news. But then there is also issues that you still need to train a surrogate. And if you're training a surrogate, you have all of the problems of training classifiers. So if you train badly your surrogate, maybe you find a lot of adversarial examples, but it's because your model sucks, and not because it was easy to break. Imagine that you have overfitted completely a model, and then just by changing the input by a very, very tiny bit, you end up in another, in a local minimum or maxima. But this doesn't happen when in the target, because they are really trained in a different way. Again, I said that for many domains, the data might be available, but also data might be incredibly unavailable. Think about medical records. You can't browse Google and say, hey, please, Google, tell me all of the medical records of people with this disease. Of course, these are totally unavailable. And if you want to apply a transfer attack against some sort of, of a classifier on this domain, that might be hard. And finally, if you want the labels, you still need to interact with the target. So there is a phase when you send your sample to the target and you wait for it to score them for you. And this might be tricky, because it might not scale with the number of data you need. So, okay, let's say this, okay, I've convinced you that, I mean, you're happy with using gradients, but now you understand that maybe even you don't need to train again a model. You just say, well, okay, you know, fair enough. What else? Is there something more that I can do, like without really using gradients? Well, the answer is yes. What I can do is that I can create the so-called black box query attacks. So again, imagine that you have like a non-differentiable model, or the model is unavailable because it's on a remote, but then you can still ping it. Like you send them a request and they just answer to you. So what you can do is, okay, you take one sample and you send it to them. You wait for the answer, and then you can reason about the sample and the answer you received. So that's exactly it. So this is basically a rinse and repeat loop. When you send things to something, something reply to you, and then you fine tune you optimize your attack based on the answer you received. And of course, since you don't want like to cause a denial of service, which just to mention is an attack where you occupy all of the resources of the target by querying it like a lot of times. I mean, a lot of times in a very, very small time window, and the server is not able to reply anymore because there are too many requests in the queue. So since you don't want to cause a denial of service, you want to optimize the number of queries. And also imagine that there is like an intrusion detection system that is basically a system that look at the traffic and says, these these requests are kind of an anomaly, so I'm gonna drop them. You don't want to be detected. So also for this reason, you want to keep this number of queries as low as possible. And then that's the loop. So you wait for the answer and then you do something. But what this something means and how many queries should I send? Or I should send one sample, or which is the best answer? Let's try to bridge these gaps. So first of all, very simple attack is the so-called zoo or Zeoth order attack. And this paper, it's published like quite a few years ago, but still, super interesting because first of all, you don't need any surrogate. You just try to estimate the gradient of the model by sending a sample and sending the same sample that has been slightly perturbed in random directions. So as you can see here, this GI, it is basically the derivative of f of x with respect to x, the direction xi, is almost similar to f of x plus h multiplied by one of the canonical bases minus, yada, yada. But if this h is very, very small, you're basically just taking a very, very tiny step further away from your sample. And this is enough for estimating the gradient in the direction. Then, with the same exact intuition, you can compute the Hessian, that is basically the second derivative. And the Hessian is giving you the information about when the function is basically going up again, or is start to decrease again. That's from calculus, And using these two informations, you can understand which are the most useful perturbation that you should apply to a sample in order to evade the model, even if it's online. Again, this gradient is not computed as the gradient, like chain rule and whatever. This is just an approximation of the gradient based on the definition of derivatives. If you're like somehow knowledgeable with calculus and algebra, this is exactly the definition of the limit. So, there is no limit here, but this is exactly that. So as you can see here, this result is super sparse. So regarding the question that you asked me yesterday, this is very, very difficult to spot from the point of view of a human, because since this attack uses like few directions chosen at random, and since it's just applied this very, very small perturbation h, it's very difficult to understand, and you also even to see inside this mess where the perturbation is. And again, this attack has been proven successful. Okay, so this one way you can do it. So you don't compute gradients, but you estimate them in a and with a suitable approximation. What else? Well, these slides open like a huge dictionary of optimizers that, I'm not gonna show you like all of them. I'm gonna show you like only two, because there are a lot. If you're interested in black box optimization things, well, there are like, I think, books that are like this wide, where you can be as fancy as you like. But I think that here, two things are still worth mentioning. One, there's the so-called natural evolutionary strategies. So what you want to do, so you have a model that is, again, it's somewhere on the internet, you can query it and yada, yada. And you would like to compute gradients. So again, you're still in love with gradients because they're easy to use, they're intuitive. So what you do is basically you want to fit some sort of a toy model on a locality around the first sample you're sending to the remote. So taking the start point and take like perturbation of it to build basically a ball of a norm you like around the point. Then you send all of them to the model, and the model is gonna score them for you. You are gonna retrieve the label, and then what you do, you fit a Gaussian, a classic Gaussian curve on top of these points. Once you have it, you have a differentiable model that is basically somehow approximating the boundary around the point around the point you send to the detector. And that's differentiable again. So you can use, again, gradient descent, Carlini-Wagner, FMN, DDN, BB, and whatsoever. Because, it's a Gaussian, it's differentiable. So basically the attack is going to use not the parameters of the remote model, it's going to use the parameter of the of the small Gaussian you centered on this point. And then you take this decision, you go ahead, and then you repeat the process. You send these epsilon ball of samples to the remote, you wait the remote to reply, you compute a Gaussian, and you take a decision. So this might be a bit slow, because of course this requires to fit a Gaussian at every step, but it's kind of reliable, because you're basically still extracting point from, as close as possible to the real point, and this is a very good approximation of the boundary. Then Gaussians has a lot of good properties about that. So it's also, it's kind of intuitive how it works. So again, it's not random as Zoo, because if you remember 1 second ago, Zoo uses random directions. They pick up random direction to perturb. Here, they're going to use all of them, because if you sample in this ball, you're sampling points that of course might be in every possible direction with respect to the starting point. So it's much more accurate. And the problem is the manipulation might be larger, because of course you're not cherry picking dimensions, you're just taking them all. But this attack has been tested again, some machine learning as service. In this case, there are some demo that are available in Google Cloud Vision. And if you, of course, now I just put you like, okay, don't worry, I see the message, it's fine. The lesson is recorded, so you can go back and retrieve the first half an hour. So if you go to the paper, I just put you like a simple example here, where this image, where it is clearly skiing, humans, and snow, and mountains, with this attack are perceived as dog and dog-like mammal. That, it's okay that human and dogs are mammals, but I think they're quite different. And I leave you, I leave to you the judgment about that. And then, of course, you have all of the other, but still the decision was subverted to something else. So this is a real case scenario when you're attacking a machine learning as a service, with some of this attack. So, okay, but then you're gonna say to me, okay, Luca, it's nice, but I don't want to impose a Gaussian at every step, compute gradients, and then impose a Gaussian. This is long and unnecessary. And you said, you're right. So what you can do is, we can take what nature has made with us for a quite long time until now. And these are the so-called genetic algorithms. So I think you might be, maybe you're not seeing, you have not seen it by now, but all of these algorithm works as nature works. So you take the fittest candidate to survive and you let them breed together to evolve and create new generations of fittest candidate that they breed together and evolve and yada yada. Of course, we can't wait like thousands and thousands of years like it happens for us because I have a computer now and I want to attack that model yesterday. So what I do is that I take endpoints around the starting point and I send them to the detector and I wait the detector to score them for me. Then what I do, I take the sample with the best scores and I breed them together. So like chromosomes, I take them, I mix them, and then I apply some random mutation on them. And then I just repeat the process. So what happens at the end is that if the goal, if the function you want to optimize is shaped in a good way, then you're able to steer evolution toward the point you're happy with. And you're going to end up with adversarial examples because these, the genetic optimizer will take care of like discarding all of the points that are not suited for evading the classifier. But otherwise, you're going to keep all of them that might be very likely to evade the model. In this case, there is no gradient at all. So you can see this as a like not mathematical at all approach, because if you look at like the code of a genetic algorithm, it's just send thing, mix thing with some random parameter, and replicate this for like n times and repeat. That's it. There is nothing else. So just to recap, of course, again, black box optimizers are a lot. I honestly don't know how many of them are out there. So these are basically, I just listed 3 of them that I think were relevant to the cause. But again, if you go to the literature, you're going to find, I don't know how many papers on that. Like if you just go to Google Scholar and type adversarial machine learning black box, be ready to be flooded. Just, for the brave ones that are going to do that. So just to give you a recap on the black box attacks, the benefits is that you're bounding the queries because you don't want to send a lot of them. You just sample like endpoints, and then you just compute things to approximate the direction, and you're good to go. And these optimizers are very suitable for real target in the real world, like machine learning as service. And then, as I said, there are a lot of ways for estimating this thing. On the contrary, the problem is that decisions are local, because if you sample endpoints around that single point, you're basically just estimating the boundary or the decision function in just that small epsilon ball. And that might not be enough. And not only that might not be enough, this is problematic because if you had the model with the gradient, that would have been incredibly better, because gradient already points to the direction you want. These might not, because it depends how you sample the points inside the ball. And if you're lucky enough that you sampled the right samples. So imagine that you have a function that is not smooth, but it's just, up and downs. And then you have these epsilon balls, and the points are on the hills and not on the on the depths. And that's a problem, because then the local decision is going to think that everything is smooth, but instead this is not the case. So that's a problem. And also, it's not that I lie to you, but I lie to you. It might happen that the number of queries will still grow like unbounded, because maybe it wouldn't be enough few iteration of this algorithm. We might end up with like repeating them over and over and over until you find an evasion. So I take a sip of water because I need it. And before going further toward like another part of the lecture and asking you if you have questions so far about or curiosity. So far, so good. Did I kill you with these slides? No, it's fine. So I hope I didn't, I didn't like, flatlined most of you just with like all of these talks, but just to shake up a bit, let's now talk about something different. So this is the whole picture. Gradient-based attacks, and you're happy with gradients. You're not happy with gradients, so use black box attacks. Now, is there a way that the attacker can do something totally automatic? I think that you might have guessed that these things requires like a lot of parameters, like the number of points you need to send, or the step size of the gradient, or the norm to use. You can be as wild as possible. So are there some already benchmark tools that can help me steering all of these choices? So there are two answers on that. The first is that you can automate attacks. So in 2020, there's been published this paper called Reliable Evaluation of Adversarial Robustness with an Ensemble of Diverse Parameter-Free Attacks. Short name, AutoAttack. What does AutoAttack do? Basically, AutoAttack is a collection of attacks that are applied automatically one after the other against a particular model. So we are switching from the attacker point to the defender point, and we want to evaluate our own model. So we have it, and then we want to say, okay, let's try to understand how these things works in the real world, and how much should I sweat if someone breaks it. So without attack, what I do is that I just open this black box magical tool that is going to test like a lot of attacks, and with a lot of, with a sort of parameter tuning, and it's going to say, okay, the model, the robust accuracy of this model is this one. And inside this box, there is also auto PGD. So if you remember Project Regarding Descent, what auto PGD does is basically the same, but it also understands how to tune the step size of the gradient while it's optimizing. So if auto PGD understand that it can increase the step size and going further, it does. This saves a lot of time to the attacker or to the defender that want to test a model, because you don't need to run attack, see that it fails, go there, and yada yada. So the problem is that there are some basic auto-tuning techniques. So there is not something that is that can work against these things can work with simple model, but they might fail with models that are more complex or models that are maybe robust to PGD, for instance, but you should need some reverse engineering of the defense and adapt the attack to the defense. So AutoAttack is helping because it's just doing some basic tests. Then what you should do, you should go be more brave and fancy and start to understand how this defense works. And for this reason, what people did is that let's take all of these models and just put them online in these so-called robust bench. So robust bench is a place on the internet where people publish publish models and say, oh, my model is very secure, try to break it. And then they use AutoAttack and they see how the performance vary with respect to the results of the paper, because of course the results on the paper might be very different from the real results. Now it's not a trend anymore. Now the models that are robust bench and are evaluated with AutoAttack basically are already at the same level of the evaluations that are conducted on the original paper. But that was not always the case. And exactly for this reason, the good thing is that you use blindly AutoAttack and you're happy with that. But the problem is that might not be enough. So for instance, let's consider this. You have a model, and this model always cut a part of the decision. So if it's more than 8, I just raise some flag. If you use PGD as is, you might not evade this, because PGD is not aware of the fact that this model is doing something maybe not even differentiable, or maybe they're doing just something fancy. So what the attacker should do, or in general, what a person that created a model should do to be fair about the results of his models. So let's deep dive into the world of adaptive attacks. So what's an adaptive attack? To answer this question, I'm going to show you the next slide. This is basically the timeline of defenses that has been proposed to mitigate adversarial attacks. Like, I mean, if how many of you remember like the distillation defense that I told you yesterday? I mean, has been published in 2060, and then like a lot of them. Here there are just some names, just to let you understand, just to visually understand that there is a lot of interest of creating defenses. But then, at some point in time, Carlini, like authors like Carlini and mostly Carlini, started to break these defenses, because the point is that yes, your defense is secure, but it's not secure against an adversary that knows your defense and try to reverse it and create an attack that takes in consideration this defense. So now I have the classifier that, like, remove, as I told you, as a threshold on the score. And now my PhD knows this. So instead of maybe raising the score up to this threshold, it still goes down and, try to get past to these rough detection mechanism. So after breaking, I don't know how many defenses, at some point they started publishing some guidelines. So instead of saying, guys, please don't publish defenses as is, try this, and that before. After this, basically they ignored him, because basically nobody was, everybody saying, yes, that's important, but defenses were still published. And that happened again. So people were, putting a lot of effort in, I can do super fancy statistical models and rejector and whatever, but nothing were working, because again, 2020, again, Tramer, Carlini, and other people just published another paper saying, guys, no, this is not working. And again, they published some guidelines. Again, please don't do this, please don't do that. If you have an attack, do this, and that. So this is basically an arm race. There are going to be like defenses that are going to be published from that point on that are going to be broken in few papers later. So to bridge this gap, at some point, someone trying to do the so-called deep sec. So they basically took every attack, they took every defense, Cartesian product. So they tested all versus all. And as you can see in this plot, in this table is this, sorry. As you can see in this table, you have basically all against all. You have like different norms attack, different attacks, so FGSM, BEAM, PGD, and deep full, and whatsoever. And then you have like all of the possible models. So you have a lot of defenses that are going to be covered later on in this course. But this slide is just for, the takeaway point of this slide is, gosh, what's the best attack against the best defenses, and what's the best defense against which attack? The problem is that these are not adaptive attacks. So this is just, okay, I take FGSM as is, I take this defense and I see what happens. And this is not the way you should evaluate things, because this is going to give you a false sense of security. It might, you might think that, for instance, distillation is secure, but no, it's not, because they prove that with an adaptive attack, distillation goes down to 0% of robust accuracy. So this DeepSec paper was an interesting starting point, but it do not give the intuition about how an attack should be adaptive or not. And so what people should do? People should create adaptive attacks. So it's an eternal, if you work in security, it's basically the eternal arm race between good guys and bad guys, or in general, from attacker and defenders. So the defender design something, then the attacker try to break and do the attack, and then the defender say, oh gosh, you break my model, and you keep repeating. So instead of waiting for others to attack your model, what you should do is that you should, be one person with two split personalities. You should be, first of all, white hat, and you create like a system that is suitable for defending, and is a very, very good robust accuracy. Then at some point you switch the light, you put the hoodie, and you try to break your model. And by trying to break your model means you understand how the defense works, and then you try to create an attack that leverage the fact that you know that how the defense works. For instance, on distillation, what Carlini did is he removed the softmax layer and he used just the logit because he understood that that was exactly causing the model to be basically a step function. And then that should be the loop. You attack it, you harden the model, and then you attack it, and then you harden the model. And then in the paper, you say, okay, now this model is robust in this way. And I know it's going to be broken somehow, but that's what I do. And in this sense, the evaluation is going to be better. But again, can I do something more? The answer is yes. So the last couple of slides are going to cover some work that is like current research, by the way, and is basically trying to bridge the gap of how can I create an attack and, sorry, how can I conduct an attack and how I can debug the attack and understand if the evaluation that I carried on is fair or not. So with this in mind, I mean that most of you, code, and when you code and you have like, a program and there is a problem, you debug it. So you put a breakpoint there and you say, oh gosh, that's division by 0. I didn't see it. Thank you, debugger. Thank you for raising me this exception. I'm not going to do that again. Of course, it's going to happen like 100 times, but the concept is the same. In machine learning, what does it mean to put a breakpoint? Or what does it mean to debug a statistical model? Well, that, it's fishy for me. It's not that easy. So what you can do is you can think about all of the problems that you might have, like you might have implementation problem, or your attack might not converge to any local or maximum, or then you might have converged somewhere to something bad, or maybe the attack again, as told before, is not adaptive. And depending on these things, you can combine. You can somehow measure these guys with indicators that are the so-called indicators of attack failures that basically was the culprit of the failing of the attack. And you can use them to understand, to discern the fact that the defense is robust from no, it's the attack that has been done in a bad way. If you understand that your attack is bad, is badly performed, you can fix it and create a more powerful attack. And then you have a fair evaluation. So just to give you an intuition, so let's take this model. So this K winner take all is a model basically that it's super noisy. So when you do one step of gradients, you might end up in like random directions. So they evaluated it and they say, oh, it's robust. But the point is that it was not that robust. The point is that it has like a lot of problems. And with indicators, you could have seen him before Carlini arrived and broke it. And the developer would have said, oh, sorry, I forgot to see this, and that. And the same thing for like many others. So if you're interested in like understanding what the debugging means for adversarial examples, here is the reference of a preprint like we are still pushing, and we are still doing research on. So this concludes the part of evasion attacks. I hope you you kind of enjoyed it, and I think we can do a break until until 4 p.m. But I'll stay here if you have questions or curiosity, because after this, we're gonna switch completely topic and we're gonna deep dive to another word, which is the word of, computing adversarial examples, but in a more security-driven domain. So see you later. If you have a question, I'm here. I'm just remove my camera and my microphone in the meanwhile. See you in 10 minutes. Okay, hello again. So while I wait like for a few more like seconds or like 1 minute more, and then I'll start with this part of the lecture. First of all, just to understand which background you have, like computer scientists, computer engineering, just to understand, because here there might be some technical things that I might, want to explain more or less depending on the background. So if you could let me know, also because I'm also curious about that. Okay, we have one computer engineering. That's it. I think we have like only. Okay. 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 So now, for now, like all computer engineering, nice. And okay, computer science. Like, I'm a little spoiler. I'm a computer scientist, so I'm infiltrated here. Anyway, so mostly from computer. Oh, applied mathematics. That's nice. That's very nice. Very, very nice. So, because this part, I would also try to, I'm gonna ask you like a few things, and just to try to have a chat about that. So, as you can read from the, from the title, this is adversarial examples, because we are gonna deep dive into the creation of adversarial examples in the domain of Windows malware. So first of all, for the one who doesn't know, XE is the extension that is appended to every executable files on Windows. And if on Windows you don't have the .exe at the end of the file and you double click on it, the Windows builder is gonna say, no, I can't. I don't know how to open it, because this is how Windows deal with the extensions. And these are very small details, but these set the pace of this lesson. So interrupt me when needed, like things maybe you didn't understand it clearly, because here there are going to be like some very, very not mathematical low level details. So let's just deep dive. If I click on the slide, of course. So first of all, and this is a question that I'm going to ask you, what are the different, how programs and images are similar? If some of you, wants to guess. So you have a program and you have an image. How these things differ? There are no right or wrong answer. Just shout out
programs one. As instructions.
Mm-hmm. Yes, exactly. So first of all, so I'll just add a slide more about that. So both programs and images are encoded in bytes. So what is a byte? Basically, a byte is a number from 0 to 256, and it's basically stored in 8-bit. Okay, sorry, no, oh gosh, start doing bad things. No, yes, sorry, it's 8-bit. Okay, so you have like 8, 1 or zeros, and these are just 1 byte. And both programs and images are encoded in bytes. So if you take an image and you open it as a file, you're gonna see basically, and it's an RGB image. So from the signature, okay, let's expand. What do you mean by signature? Because that's a nice, that's also like another nice thing. What do you mean signature? If you want to like say something about that.
Images, for example, start with I don't know, PNG, JPEG, and ends with their relative bytes, while, for example, executable starts in Windows with the signature PE. So they are different.
Oh, yes. Okay. So, they start with another magic number, but that's exactly another thing. And I'll cover that. So first thing, I mean, these guys are also made with bytes, all of them. If you open them with a file editor that shows you like bytes, so /x, whatever, you're gonna see this guy that you see like on the right side. But then the problem is that, first of all, they have different file structure. So as Silvia said, images have, the structure of an image that is saying, okay, this is a 3-channel saved image, which is a red, green, and blue. And the other is that, no, this starts with a special character saying this is a program, and there is a structure. And then, as I don't remember who Andrea maybe said, the programs as instructions. So instruction is not something as continuous as image. So if you imagine that you take like the picture of my face, and then you compute like the gradient of this pixel, this somehow points you in the color space somewhere around, pale, very, very pale white, because I'm super pale, I'm sorry. And there is a direction. But what does it mean to compute the gradient of an instruction? I mean, it's not even a space. The byte of a program is actually a categorical variable. So think about also like the ASCII table. What does it mean, the square root of character A minus character B? Absolute nothing. So that's the very, very first problem you have. You don't have a metric. You don't have a way for telling you how much distant I am from point A to point B, because there is no notion of distance here. So that's the first problem. Second problem, format constraints. So as I told you, and as foresaw, but by like one of your comments, images have some structure. So again, you can take like this photo and you add some noise, like the summation. You just impose some sort of noise that you computed with this whatsoever attack. You end up in a very, very nice image, which is, in a machine learning domain, is recognized as something else. Then you want to do the same thing with a malware. So this is exactly, this is the very, very super trustable program that someone gave to you with a USB pen. Like, hey, this is like the cracked version of Cyberpunk 2077. That's cool. Play it. It happened to a friend of mine. I'm not even joking. And then they sum some adversarial noise, and then you produce like an adversarial Cyberpunk 2077. But guess what? This doesn't work anymore, because there is some structure that is super easy to break if you perturb just one byte in a bad way. So that's the second person. First problem, there is no notion of distance, like the LP norm. What does it mean to have an LP norm of a code? Second thing is you have format constraints. So you can just alter the bytes as you liked as for images. Third thing is functionality. So if I take a program, okay, and I do some, let's say that we have adversarial perturbation, okay? I'm not telling you what it is. You know that you can do it, but then the point is, how these two guys, so again, if I should ask you, but the answer is already inside the slide, what should happen? This adversarial version of trustme.exe, what should do with respect to trustme.exe, the real one? So I have perturbed it, and it doesn't, it shouldn't not break. But then what's the important thing about that? Just take a sip of water. Maybe the same, but yes, it's the same, but with something more. But since it's a program, what is the thing that you should not, it's a malware, it's a ransom. Imagine this is a ransomware and you perturb it. What you want still to be there. So for the one of you that are like me, that I really think about bad things every day because I work in the security field, these two guys should do the same thing. Yes, exactly that. You don't, I mean, you want the adversarial trust.me.exe to be still around somewhere. I mean, you don't want to destroy its functionality. You want it to be as malicious as it were, but with the evasion capability. The point is that many things in research do this. So they take like a whatsoever manipulation that might break the format and also the functionality, and they apply it to the malware. Then they put the malware inside a virtual environment that or a sandbox. So what is a sandbox? A sandbox is a virtual machine that with some analytics tools that trying to understand what programs does. And if such trust.exe adversarial is still malicious, it's gonna say, hey, it's still malicious. So you can repeat the loop. The problem is that this, I mean, you should, since it's malware and basically it infected your virtual machine, you should restart the virtual machine. And you have to remove all of the things that changed and keep it like at the initial state. And if you remember what I told you about gradient-based attacks, you might end up with many iterations. So it means that at every manipulation you apply to the malware, you have to do this. And I think you might understand that this might be super computationally expensive. So 3 problems. The no metric, the functionality, and the format. So what the attack should do, from the point of view of the attacker, what I should do. So I am the attacker and I want to infect this phone, but this phone has some machine learning. What should I do? First of all, I should study how programs are represented as a file. Because if I know that, I know also how can I exploit the format to my own advantage. Then I can create some, I call them exploits, but they are not really exploits for the security. The people that, did a bit of security, this is not like an exploit, like a buffer overflow. But intuitively, this is, you can bridge the gap between the things and intuitively thinking about something similar. So you want to craft something that you put inside your malware, and this is gonna be like the thing that makes your malware evasive. Then lastly, you have to choose how and what to inject. So taking a sip of water because it's getting, sorry. So first part, we start by asking ourselves how programs are stored as a file. So that's the Windows PE file format, as some of you already said. So first of all, let me just do some history because this object is kind of cute from my point of view. First of all, it's adapted. So it's not as that when DOS, that was basically one of the first operating systems created by Microsoft, was created, it was already this format. But they adapted it through times. So this has been introduced with Windows NT 3.1. I don't remember exactly roughly how many years ago, but 3.1 is very, very far away in the past. And before that, there were other formats, and one of these is the DOS. So basically what they did is that, so this is the DOS, then there was the COF, and then there was the P and yada yada. And then they stopped because come on guys. And basically they piled piece of formats here and there to keep the retrocompatibility. For this case, they still, so if you, I think that some of you have a Windows machine, and I'm gonna tell you something very strange. In each of your applications, there are at least 200 bytes that are totally useless. And useless in the sense that they are the so-called DOS header and stub. What this guy does is just saying to the operating system, is just saying to a DOS operating system that that program is not a DOS program. So if you have a virtual machine with a DOS operating system and you launch paint.exe, on the command line, you're going to see this message. So this program cannot be run in DOS mode. This basically is encoded inside the DOS stub, which is basically some machine code, machine instructions that prints this message to the screen. And the only relevant part, as some of you already said, are just the signature, which in this case is MZ, and a pointer that is like a pointer to the real PE header. So you have just like this, and so this offset here is at like offset 60, which is 0x3c, and it's done. Everything else in the middle and after is totally useless. So I think that after these slides, the perspective that you're gonna have on the Windows operating system is gonna change a bit. I'm sorry, and not sorry at the same time. So just like to warn you. So finally, we land to the real header. So again, there is the offset that points to this signature, which is P00, as someone of you said, and I'm happy to be honest that someone already knows that, because it means that they already either deep dived inside, the format, or they did some reverse engineering or whatever, because it's very fine with this field of adversarial machine learning. So if you have some background in that, you're gonna be like, it's gonna be like a bit easier to understand these kind of things. So this header is the real metadata of the header. Is the real metadata of the program, and it basically describes the general information of the file, like which kind of machines it runs on, or the number of sections that I'm gonna describe you later, or other metadata and other things that like you can find them on the internet for easily. Then naming, I'm honest. When I was studying these things, the naming was totally obscure to me, because the real header of a program is this optional header, which is not optional at all. So basically, it's called optional because, so for the one that are familiar with compiling, when you compile a program, you create like temporary objects files that only contains like the code or the data that are linked together by the linker, and then this header is created. So it's optional in the sense that it's not put inside the temporary objects that are created by during the compilation process. But again, it's not optional. It's in every programs and in every DLLs that you have on your system. But this is basically where the juice lays. Where the real juice of the metadata lays. And here you have basically what is used by the operating system to load the file. So the loader, which is the program that is in charge of taking this structure and put it into your RAM, you're gonna find most of the information here, like where the APIs must be imported, where the resources are, or how many bytes it has to load inside the memory, or which is the alignment of this file. So where the loader should find content by multiplying this number by a fixed amount, and it's gonna say, okay, I'm gonna jump by like 500 bytes, and I'm gonna find like the code, and then I'm gonna jump again by another multiplier of that number, and I'm gonna find the data, and yada yada. So after this optional header, there is the last part, which is gonna it's not the last part, but it's just a recap on all of the part that I'm not telling you. That is the section table and the sections. So section table is just a data structure containing the information for the loader, again, where to find the code and where to find the strings or the resources and yada yada later on in the file physically. So each section entry is connected to a section, And the section contains the content itself. So you can imagine that you have like so this is the header, section entry, then section 1, 2, 3, 4, 5, 6, until how many sections you have. And for instance, every section has a name, and this name is 8 bytes long at maximum. And then if it's more, there is like a data structure that says, okay, if this is more than 8 bytes long, you should point to that part in the file, and the name is extended. But anyway, so the code section is oftenly referred to .text. Again, naming things, don't blame me. I honestly don't know. It's just Microsoft that is, doing, juggling with things. Then you have like error data, which is read-only data. Then RSC, this is like icons because are resources, and counting. So if you have any questions about the Windows PE file format, just because I need to take a sip of water, just ask me now before deep diving to the loading part. I think maybe okay, let me just briefly conclude this, and then I'll just give you like a few minutes for the questions. So now I told you about all of the DOS header optional sections and whatever, and the loader. Then how programs are loaded into memory. So first of all, I want to thank this guy. So this guy, Angelo Bertini, do like a lot of research in like explaining file formats and breaking them. And it was like a real inspiration for this kind of work, because he's really, he can do like, creating PDFs that are also like HTML pages, that are also executables, that are also images, that are also in another embedded PDF that are videos. I'm not even kidding. You can find like some of his videos online, and I really suggest you doing this because they are fun. And so one of the things that this guy also do is creating this very, very cool recap on how things works on the low level. And that's how the Windows loader works. So first of all, it parses the DOS header and it finds the PE header. So it's like what I told you before. Then it parses the PE header and it finds the optional header. And it parses all of the information about how many bytes loading into memory and where to look for what. And finally, it arrives to the section table. And it counts how many sections are like stored in the header, and it starts loading them in memory based on the information that are stored inside the section entry. And as you can see here, basically they are mapped into memory depending on their size and on a file alignment. A file alignment tells basically in RAM how much things should be they should be, how can I say, divided. So you have like 1K of bytes for basically each thing, and then you keep doing that. So basically, from a compact representation is gonna explode inside memory. And then, it parses all of the imports that are like the function imported from libraries and operating system, and ta-da, you have your paint.exe programs ready to be started. So if you want more information about this, there is some literature on some books published by Microsoft, but I'm gonna warn you, these kind of things are kind of obscure because of the closed nature of the Windows operating system. If you I don't know if you do some reverse engineering on Linux, there are a lot of resources online because everything is open source. Here, the word is obscure, and it's difficult to understand maybe things that works and do not work properly. Because you can't read the code. So either you reverse engineer the Windows libraries, or either you find people like Angelo Bertini at some point create like fancy plots for you, and they are super, super beneficial. At least for us or for me that I work in this field. So this concludes the part of the format and question time. So now I'll give you like 1 minute for questions, because I think I put like a lot of juice on the table, and I'm gonna build everything on top of what I told you. So this might be a good time if you need. Okay, I assume that everything was clear. I'm happy. So, okay, now remember the three things that we should check. So we should check the format. Now we should check how we can bend the format to towards our goal. So our goal is to add content, inject content, manipulate what has been what's already there in order to land evasion attacks. So we don't need to forget that. How we do that? And also we want to keep the functionality preserved. So how we do that? Well, we do this with practical manipulations. So what a practical manipulation does is that you're changing the representation of the file, but you're keeping intact the functionality. So you're taking two birds with one stone. You're still preserving the fact that the ransomware is a ransomware, and then, but then the way the ransomware is stored in memory is different. Just to give you an example, if you take these two images, I think that most of you are going to be super confident that they are both token, right? Even if that is shifted by 90 degrees. If someone thinks that the one on the bottom right is not a token, please raise your hand and we'll have a chat just to understand that I should change slide. But in case, if every of you is convinced, these are still token. Maybe you should do this to see it properly, but it's still a token. But that's exactly what I want to do. I want to change, in this case, I didn't change the format. I changed the value. I transposed them. But these are images. How can I bridge the gap? So instead of going further on the slides, what would you do? So if, I gave you like some intel on the file format, and there are some low-hanging fruits that you can, take to understand. If you can like reach with already the information I gave you. So what you would, take the hat of the attacker, what would you do? There are, again, no right or wrong questions. Try something. Also, if you want to use the chat instead of voice, it's gonna be okay. Yeah, so the point is, you are the attacker. You have the Windows PE file format. So you have this guy. And you want to perturb it. Let's forget about for the adversarial part, but you want to perturb it. And in the things that I told you, there are at least a bit of, some pointers that I left dangling there that you can use, to mess with this guy. So if you're the attacker, what would you try to do with this format?
Maybe try to modify some bytes in the data section.
Yeah, that's something that you can do for sure. Yeah, so you can modify things inside sections that you know that are not used. Yes. Something else?
Maybe modify something in the DOS header and stub, which is not used at all.
Okay, that's exactly the first thing I wanted to tell you about. And on the section, I'm gonna cover it later, but it's still there, don't worry. So first of all is that, gosh, guys and girls and people, this guy is exactly an adversarial farm. You can put whatsoever inside it and nobody, will notice, but from the point of view of a machine learning algorithm, you won't notice that because you preserve the signature and Z, you preserve the pointer, and everything that is in the middle can be perturbed in the way you want. So this is exactly one adversarial attack that you can do. And just to mention, so this part, so from MZ to the pointer are just 58 bytes. And basically there is a paper that has been published that said there is this deep learning architecture, and by editing only that 58 bytes, you decrease the robust accuracy from 100% to 0 with 58 bytes. And I'm gonna cover it later, but just to give you an intuition, this is the exploit I was telling you. It's a way you can perturb the file and still, be malicious, because as I told you before, the loader doesn't care about what's here. Even in the DOS tab where there is some machine code, this won't be executed by nobody in the world. It's gonna be still loaded in memory. So these things are still in the memory and it's fine. But they are also mapped in a region that is not executable. So even if this opens like a reverse engineering and CTF style part. If you would have, you could like insert like also a shellcode here, an exploit, if this thing would be mapped in a executable memory, but this is not even mapped in an executable memory. So, oops, what you can do, so from this point, so remember that you said you can perturb the DOS header. Okay, now I'm gonna give you like one hint, and I'm gonna try to leave you guess what else. So here you have a pointer to the real header. What you can do with that pointer?
Maybe move it.
Yes, exactly. So the point is that there are some constraints here and there that you can do, but still this is 4-byte long number. 4 bytes is huge. Like, it's you can encode like a very, it's an unsigned it's a short integer. No, it's an integer. Like, you have like a lot of, you can encode like a lot of things with 4 bytes. So what you do is you craft a point, you craft like a value that is good enough for like some other constraints that you have with the format that I didn't explain to you because like they're kind of tedious and you can find them online. But just to give you the intuition, you enlarge this, and then your DOS stub, instead of here, ends here. And again, you can inject things inside it. Of course, this content is gonna still be loaded into memory, but as I told you before, is inside the header, is not mapped in an executable part. So you're free to some extent. Okay. So now I'm gonna like stop like asking you to guess things, because now things are gonna get a bit more like complicated. What you can do is you can do the same thing, but with sections. So sections as a location, let's say, where the content, lies inside the file. So this pointer to raw data is gonna tell you, hey, loader, the code is like 4K bytes from here. And the loader say, okay, thank you. And then you extract and it loads in memory. The point is, everything that is in the middle is not loaded. So I'm gonna go back. If you have a look at here, as you can see, everything is loaded aligned with the pointer to raw data. So if you say to this pointer to skip like 200 bytes, these are gonna be also skipped by the loader itself. Can I also add users functionality? Yes, but I'm gonna cover it up later. And wait, sorry, let me conclude this and then I'm gonna add something on that, but good point. So what you do is that you shift the header from the first section, and then you can inject how much content you want. And the funny thing is that this is not even loaded in memory because it's gonna be skipped by the loader. Now, to answer your question, Andrea, yes, you can. So basically, you can add like an APIs inside the import library, and then you should add like a piece of code that is going to be executed, but then you should find a way to jump back to your code because you want to keep the functionality. So what you can do is, oh gosh, how much I would like to have like, chalks and just, draw things. But you have like the entry point of the executable inside your program, and it's gonna say, hey, the first instruction of the text of the text section is here. You can misuse this pointer and create a new section, and in this new section there is like a sleep function or just something else that at some point jumps back to the real beginning of the program. So this is a way you can do that, and also this is something that is also like there is a lot of literature for doing that. So if you're interested, you can have a look into binary rewriting techniques, and I'm gonna type here, and then you can be super fancy about it. There is like a paper that I've done like a lot of literature on that. But if you're interested, and it's a very, very interesting word, you have, you have the internet on your side. You're welcome. So, okay, last three manipulations, but this I'm gonna ask you again. So I told you that there is section entries and sections, and I think I already give you the answer. So what else can I do with sections? Come on, now I know you're in the flow. I know. Now it's. We are all in this together. So I think you know, and I told something while answering the previous question. Think about the number of sections. What you could do.
Can I specify that I have a different number of sections?
Yes.
And use the other to inject malware.
What do you mean, the other to inject malware?
For example, if I have, I don't know, maybe 15 sections, I define that I have only 10 sections. And I use the other 5 to inject malware. I don't know.
Yeah, so basically what you can do is that you can add sections. That's exactly the point. So you can add more. So what you do is you add another section entry, and then you add at the end of the file another section, which is the adversarial section. This is loaded in memory, and all of the content that's here is adversarially controlled. So you can control them. You can put whatever you want. You can put executable code. You can put data. You can also try to let the loader understand that it doesn't have to load it in memory by using characteristics. So depending on you can be as fancy as you want. So yes, you can inject sections. And speaking about the question, some of you said to me, you can alter bytes into data. So yes, you can also alter something inside the other sections, but you have to be super sure that these bytes are not used in a way, are not used by the program. Imagine that you have a string that is the password, and this password is encoded somehow, but it's inside the .data section. Then you perturb one byte, and the program stopped working because that string was relevant to the overall program. So usually what you should do is either that in this section you can mess around, that there is the icon, you mess with the icon, let's say, or either you create another section and then you do whatever you want. So the answer was yes and no, but now you have you know why. The other thing you can do is that, this is something tedious. So when you compile a program, the linker puts some 0 bytes at the end of each sections to maintain some alignment. So each section should be a multiple of 512 bytes. So if you write, of course, the length of the code, for instance, it won't be. Is this is this similar to a meltdown attack? Wait. Sorry. Which part?
The previous one, when you talk about the fact that you can point to another side space of memory, maybe for reading something.
Okay. No, I mean, the meltdown attack is a side channel attack. So you are trying to guess what's happening in memory by looking at other signals. But no, this is, I mean, we are kind of orthogonal here. When I was talking about when you map as executable, I was referring to the fact that you could inject some shellcodes inside the DOS header. And then what you could do is you can jump in the region of memory where this shellcode is and create an exploit. So imagine if you have paint.exe, but you're paint.exe, that instead of like when you type, when you move the mouse, instead of moving the mouse, jumps into that portion of memory and executes it spawns a shell. And that's what I was referring to. But this memory is mapped in a non-executable way. But this is not related to side channels attacks. That's another thing. But cool reference, because side channel attacks are very interesting for the machine learning perspective.
Okay, thanks.
You're welcome. I'm happy this lesson is interactive, so I'm very happy about it. So the slack space is basically a portion of content that is appended to each section in order to maintain the alignment, because the loader is picky and always wants the content to be aligned to what it says to be. So in order to maintain this, basically these are all zeros. But guess what? This content is not. So if you're the developer, let's say this, you're the developer, you don't know that this thing is here, so you don't use it. And then as an attacker, I can feel content inside it, if it's present or not. Again, this thing is loaded in memory, so you might also think about something fancy to do with that. Last but not least, the easiest thing you can do. So you forget about the format, you forget about the offset, you forget about the DOS header, you forget about the APIs, you forget about everything. You take your file, then you just append content at the end. Done. That's the most trivial things you can do to create an adversarial malware. This is not loaded into memory because it's not part of a section. It do not for sure destroy the functionality because the program doesn't even know that that thing is there, and yada, yada, yada. So I'll take a breath because, this is gonna it's kind of, extensive. So if it's okay for you, I wish to conclude few slides more and then have a break and then keep going, just taking a sip of water. If you have a question about the manipulations, you already had a lot, but take since I'm drinking now, think about it and tell me, and I'll be glad, I'll be happy to answer. Oh gosh, it's over. Anyway. Ouch. Okay, so if there are no questions, few slides more until the end, and then let's do something more practical. And by practical, you're gonna. I think you're gonna. By practical means that you're gonna you're gonna edit some few things. So I told you which is the format. I told you how to manipulate the format. Now, finally, how can I create a gradient-based attack? That's the whole point, right? I have a model. I have a machine learning model that detects malware. How can I break it? First of all, there is a problem. So for the ones of you that remembers what I told you at the beginning, bytes has no metrics, and hence it's impossible to differentiate end to end. So what the model designer do is something like this. They take all of the input, the bytes, and they project them inside a feature space. Or so this is the usual, standard learning pipeline. Then the problem is that everything is differentiable up to this feature space. Because of course, there is no metric again on the bytes. So since there are a lot of techniques that try to be end-to-end in malware, the easiest thing is to use this feature-based representation as a combination of two functions. One is cropping. So you decide that you want to analyze all of the first 100 kilobytes or the first 1 megabytes. And then you crop everything that is like from that point on. And that's already a problem, but anyway, let's forget that this is a problem. And then you project them in a space where you try to impose a metric, and basically you do embedding. So for the one of you that are familiar with like, deep learning stuff, or I think they already know it, but for the one who are not, and me included when I was studying this thing, embedding is basically you take one value and you map it inside of a vector space of more components. And then you try to learn the representation. So what happens is exactly what you can see here in this like cloud. Every byte becomes a vector. And so your sample becomes a matrix. But now you have a metric. It's not just a categorical value anymore. So you feed them into the deep neural network, and then you say, oh, if the score is like more than theta, that is my threshold, it's malware, otherwise it's good work. So what you can do, since there is like a one-to-one mapping between bytes and its embedding value, you can compute, the gradient up to the embedding value, and then you can basically take the closest byte to that embedding value. And that's how you do gradient-based attack in this domain. So you compute the gradient, and then basically the gradient is a monster because it's a matrix. So where each row is the gradient in this byte space. So in order to choose the best byte to use as a substitution, you do the following. So imagine that the Zj is the byte in this embedding space, and Nj is the gradient. So you move into the direction and you project all the bytes on this line, and then you take the closest one. Because this is not a continuous space. You might have a byte here, one here, one here. It's only 2056. It's not a discrete search in the space. So the only thing you can do, you can project things on a line and take the one that is closest, as close as possible to that one. Then you substitute, and then you repeat this for every of the bytes of the manipulations that you have, like the DOS either, for instance, or the content of a whole section, or the extent of the DOS either. And you can be fancy about it. So you can do this byte per byte. So you compute the gradient once, and then byte by byte, you do this, then you do another iteration, you compute the gradients, that's the only way you can do for computing gradient attacks on bytes. The point is, again, the robust models are not all, most of the models are not differentiable, or again, they might not be available, as I told you. And in malware, there are two very, very heavy reality check. First one, the real robust models are no deep learning. So deep learning is kind of, I think you know by now that is powerful, but it's not as reliable as we might thought. So usually state-of-the-art classifiers uses decision trees, and decision trees are not differentiable. As I told you, like at the beginning of this lecture, you don't have gradients. This is like, oh, number of section is less than 5, okay, go left. Is more than 5, go right. You don't have gradients. So that's one huge problem. The second huge problem is that models are unavailable, for sure. So most of the people, even like many commercial vendors, they use machine learning, and these machine learning models are behind a firewall. You can't reach them, but you can query them. Or either there are some online services like VirusTotal that basically collects many of them, And then when you want to do some triage or some malware analysis, the first thing you do, you go to VirusTotal, you put a malware inside VirusTotal, and you wait for all of the antiviruses to score them for you. So you don't have the model. So if you want to work in this field, prepare for the fact that most of the people are going to tell you, yeah, but you don't have the models. Yes, they're right. So you have to come up with things. So let me conclude this and then we do the break, because it's something that I already told you at the beginning of the lesson. So again, what you can do transfer attacks. So the point here is that you might find things online because there is some research and there are some open source state-of-the-art classifier. So either and also the data are, you can find data under paywalls. So if you go to VirusTotal and you pay subscription, they give you data, both goodware and malware. And basically, these goodware and malware are the same that are used by the companies that trains this model for their own business. And this is basically a good thing for the attacker because you have these data. Then, this is exactly what I told you. So you either train a surrogate or use open source model, you optimize locally, and then you do gradient attacks, and then you send them to the target. Or either, again, use query attacks. I'm going fast here because I think I destroyed your ears a lot in the first part of the lecture about it. The takeaway point is that here, if you do this kind of attacks that I explained you at the beginning, byte per byte, it's gonna take forever. Imagine that you have like 1,000 kilobytes, so you have 1,000 variables to optimize, and you want to optimize it query by query. Not possible. It's gonna take forever, and also they're gonna detect you because these guys. Now we are really working with the guy that's trying to spot you when you do something that is not good. So things are getting, pretty edgy. We are not in the image domain anymore. So that's one of the fancy things about studying these guys. So what you do to speed up computations, you instead of optimizing byte per byte, you harvest content from other samples that are in the goodware class, and you inject it inside the malware. So for the one that, for the section injection, for instance, what you do is take this is like Paint, this is Photoshop, this is like Task Manager. You extract content and you add it in a way it doesn't break the functionality, as I told you before. So I'm gonna do a small break until five and some minutes, and then we're gonna do this. So some hands-on laboratory on malware. So basically, I'm gonna show you something, interactively, and then I'm gonna share with you where you can find these resources, and we're gonna go back in. We're gonna be here at like 5, so 5 minutes past 5, and we're gonna do like physical things on malware. In the meantime, if you have a question, please tell me. One super quick note. I'm gonna refill my water bottle. I'll be back in a few seconds. If you have a question, type them in the chat and I'll see them in a few minutes. Okay, I'm back. So if you asking me things in the meanwhile and I didn't like reply to you, sorry. But now I'm back. Almost welcome back time. So before starting again, just a couple of questions. Which is your relationship with Python? I mean, so, I mean, you can also like, it's just a curiosity of mine. You can also type in the chat, or just you can unmute yourself and tell me which is. So, I mean, did you do some? Okay. Can use more projects, web dev. Okay, complicated. I totally get you. Good. Okay, some projects. Okay. So I'm okay. So I'm basically since I'm a black box attack, I'm gonna create like a Gaussian over this, and because basically all of the things. So I'm sorry for Giuseppe, but this last part is gonna basically be Python notebook exercises. Sorry, but that's like just off-topic chat. Basically, all of the adversarial machine learning community is now going to, Python centric, because basically all of the libraries are in Python. So at some point, machine learning guys use the MATLAB, and security guy use Python, but then also machine learning guy started to use Python. So I don't know, depends on what you do. Okay, no, okay, but I totally get that it's a complicated relationship. So it's just, it's when you mess with, how many of you have programmed in Lambda calculus or in OCaml or whatsoever? Because that was, a very, for the computer scientists here, Zeoth, yes, exactly. Gosh. Yeah, I really feel your pain, guys, really. And because when I was a student, I was studying, lambda calculus, so pure lambda calculus. It's like nice and fancy, but then you realize what I'm doing, and then you start I don't know. You can do a lot of powerful things, but so sorry for the digression, but that was just for saying that from this last part, that is gonna be more hands-on. So interactive is gonna be super boosted this time. I'm gonna show you basically how to create some things with some libraries that are already there. So I think you can see like my my terminal. So now I'm gonna just no, sorry. Before doing that, let me show you this. So the Python library you're gonna use. So this is not shameless self-promotion, but that's basically one of the only tools for doing adversarial machine learning on malware. It's done by me, but again, it's not a shameless self-promotion. It's a tool that we developed it because there was nothing else. And there is still nothing else around. So here there are some tutorials on. I'm gonna show you 3 tutorials today. First is again some Windows PE Insight. So there are like some Python libraries that you can use. And also, spoiler here, I'm gonna show you something on the virtual machine as well. Then I'm gonna show you how you can create both white box and black box attacks. And if there is time, I'm gonna show you a tool that you can use for creating adversarial malware on the command line, and they are still functional. And I'm gonna put it in action. I'm gonna see basically how you can destroy. Wait, 1 sec. So sorry for the thing. So in this library, I'm going to show you these 3 things. And if there is time, I'm going to show you a virtual machine eaten up by a very cool ransomware, just because it's not because it's fun, but because it's something that, might be useful for understanding the scale of this thing. So let me just let me just open this. Thank you. Okay. Sorry, I always forget about live demo. Okay, that was the thing. Okay, so first of all, there are, as I told you, there are like a lot of libraries you can use for create for studying the objects, so these Windows file format objects. So one of the best library I found online is Zeoth. So Zeoth basically is super maintained, and it's something that is also used for reverse engineering. Most of it. Could you zoom? Ooh, sorry. This is fine. Ah, you mean the notebook? Okay. So can you see it? Okay. So before going that, so Zeoth is basically a library that allows you to parse and read metadata of many objects, like Windows PE object or ELF objects that are the executable under Linux, or Match or that are basically the objects of macOS executable. And then you can do basic manipulations over that. So you can use this library to read information of that are contained in the Windows PE file format. So here, this is gonna be, let me just copy this path. I can do it. See if this is, intelligent enough. No, it's not intelligent. So it should be data / sorry for this, data malware sample test folder. Okay. Okay, so basically with this instruction, so now in exe.object, I have all of the information and all of the metadata of this file. So just to give you an intuition, the Petya is around somewhere. So I'm not sharing this. You can find it online, but I'm not sharing this because if you accidentally open this, buy to your computer, like that's why. But you can find malware samples online. So executing this, now we have this object, and as you can see, I have set up some. It didn't load. Sorry. Data malware samples test folder petya.file. I hate when this happens because it happens a lot. Because there is sorry. Oh gosh. This is the problem of live demo, Dot. No, because I can't. This is the problem of live demos. Okay, I'm gonna use like the absolute. Thank you, macOS. Okay. So this is okay. I can do this. If I can type it correctly. I'm not accustomed anymore to. Oh, okay. Sorry. Live demos. So basically, you can print information about it. So you can print like the information about the DOS header, or about the PE header, or all of the optional header, and like the section and its characteristic. So this library is very, very intuitive. You can find, it has like a very, very good documentation, and you can explore things. Then what you can do is that you can manipulate new things. You can add new sections. So in this case, I create like a lief.p.section that is called new sec. And the content is basically this string. So this is my newly created string encoded as integers because lief wants the content to be a list of integers. I don't know why. Then I instruct the loader that this should be like discardable. So it should not be, it's not needed to be added in memory. And then I can add this section to the object. Then the section is in place, but I need an object that builds the new executable. So this is just some boilerplate code you can use. So you create a builder, you pass the object, and you build. So if I execute it, you can see here that you have a new section with the content you wanted. So this is basically super useful when you want to do adversarial attacks, because this is exactly the section injection attack. So the lief library already take care of adding a new section entry, and it takes care of adding the content, and it takes care of mixing all of the thing in a good way. So, and then you can also you can also save it to file if you do something like builder.write like new exe.file, and I executed it, and I go back. I can't zoom a lot, but here there is the new file. So I created the new example. I don't know, maybe there's a magnifier in Mac. I don't remember. So here there is the new executable file. So, and then, it has like 2 new sections. So, because I added it twice. So this thing, this is a very, very cool way, an easy way to mess with the file. But then all of the manipulation that I told you are not implemented inside it. So for doing that, we should open the other notebook, which is the one from the attack tutorial. So let me take a sip of water, because this is my first class in ages. So I need to train my body. Anyway, so this tutorial, is gonna contain boilerplate code for using the library that I'm developing for attacking an end-to-end classifier. So if you remember, I took that when I told you about the end-to-end network that takes in input like 1 megabyte, and then it generates a score. That's exactly the point. So in this case, I'm gonna use a network called Malcolm. Malcolm is, it's a deep neural network that takes an input like, did you develop some tutorial also in TensorFlow? Me? Okay, I'm gonna do this image for letting you understand. So this is me, and this is TensorFlow. So no, I don't develop it that in TensorFlow. Everything is on PyTorch. And because PyTorch is much more handy to use. That's the only reason. I wonder why operating system permits to create new section. Why do you use it? Well, it's not the operating. Wait. Let me recap on that. It's not the operating system that is not allowing you. Is the format. You can. So if you think about the format as let me just take it like the. If you, let's just go to Wikipedia. Just to, come on. Okay. It's not the operating system that is constraining you not doing it. It's the format that is loosey enough that allows someone to inject things. So there is like no, how could you stop? I'm reversing the question. How could you stop that? How could you stop a client for messing with the local files? This is basically the same problem with like, with websites. I mean, if I inspect this and I delete this, I mean, this is only on my, I mean, it's on my machine. I can do whatever I want. How can I stop that? Long story short, I think you can't, but I mean, we can discuss about it. The real answer is you can't constrain the user not doing it, because it's not it's not a check that you can enforce at the operating system level. The operating system is just taking your file and executing it, and the only thing that it takes care of is if it's broken or not. That's the only thing. I hope I answered your question. So, okay. So this is malconf, and we can, we load it inside the, we can load it inside the, with the SecML malware. So in SecML malware, I have already imported the weights of this model in PyTorch, and then I wrap it in a classifier that is digestible to the SecML library, which is one component, one dependency of my project. Okay, I have created the malconf and I encoded it inside this, and I already loaded I loaded everything. Now I can choose an attack. So for this tutorial, I'm gonna choose the DOS editing attack with only 58 bytes of modification. So here you import the attack. That is called, C header evasion. Okay, naming is my bad. I could have called that like DOS header evasion. I might, add some wrappers here and there, but right. By the way, if you want to have a look at the code, it's freely available on GitHub. It's open source. You can fork it. You can start it. You can also open issues and put a request. I'll be happy. When someone emails me that is using this, I'm kind of happy. But anyway, so I instantiate the attack, and I'm saying that I want just to use 50 iteration of gradient descent, and I just want to optimize the first 58 bytes. And the classification threshold is 0.5. So now the attack is created, and remember when I told you about like the attack that takes only 58 bytes? So that is the guy that is not secure. And now here there is like some juice to like take all of the things that are inside this folder and executing it. So I'm just here is just some boilerplate code to encode, to load the malware and just creating the structure. So if I execute this, it's gonna, so it's gonna add the malware, inside this matrix X, and this is the score. So the PTR ransomware is like 0.91%, 0.91. So it's 91% probability that this is malware. And this Satan, which is another malware that I don't remember actually what it does, because I always forget. These names are not, effective for remembering what they do. But this, because I really work a lot with this guy, because it's one of the malware. It's my favorite malware, first, let's say. So both of them are saw as malware with a high confidence. Okay, so now what we want to do is we want to run the attack and see what happens. So for each sample, I just run this attack to see what happens. And basically, this is it's still running, so I'm just waiting. The point is, under the hood, the attack is doing, is computing gradients and is, pointing to the direction of maximal ascent, is manipulating bytes, is doing all of the things that I discussed to you before. And these are, I don't remember what, but I think it. So this should be the final score. I don't remember why I put it this way, but anyway, let me just shrink it up. The other, I don't care about like all of them. I can just use the first one. So let me just use this because it's easier. No, he's right. He's right. Let me just load only one malware. Okay. So just, you know, to be sure what I'm looking at. Okay. So basically, this is the score of the classifier. So it started from, so basically this dot confidence is telling you like iteration per iteration what happens. And so this is like the starting point, and this is after one iteration of the attack. So it drops from 91% to 6%. I mean, that's kind of scary from my point of view. So then what you can do is, okay, now I want to recreate the malware, and I mean, the real malware. So I take this and I save it as a disk. And now I load it again. And as you can see, the score is the same. So with this function, create real sample from adversarial, what you do is you're creating an adversarial, I mean, you create the malware from the adversarial example. So if I go back here in the data structure, I don't remember where I saved it. So create file names, add. Okay, I don't remember where I saved it. Ah, no, sorry, I didn't save it. Sorry. So to physically save it, you have to, like, if I'm not wrong, you have to specify something here, like the output name. I mean, I can check it later. And then this is gonna create like the real adversarial malware, and you're done. So this is enough for like white box attacks. Sorry for, like, you know, going back and forth a bit, but and I understand that this is kind of verbose, but after you understand how things works, you just go more. I mean, you just go fast in the process. So if you have a question so far, I will go to the last tutorial and I mean, you know, even if we are gonna like conclude earlier, it's not gonna be a problem. But I mean, I just wanted to show you like two things more, just to give you like a real feeling about these kind of things. Questions so far? Okay, I mean, I can just briefly go to the tutorial. So, okay, last part of the, black box tutorial. So we don't have gradients and yada yada. This time we are still gonna use Malcolm, but we are gonna forget that we have gradients. So imagine that this is online. So so this is just some boilerplate code for wrapping Malcolm in a classifier that only exposes the predict function and nothing more. So from a code point of view, you can't create, you can compute gradients on top of it. But the only thing you have is the score. So I create this and that, and now I'm creating. Okay. So I'm gonna create an attack. I'm gonna use this attack that is basically a section injection attack that is gonna take, as I told you before, content from goodware. So in this case, in this folder, I put some goodware, so like Paint, Calc, Word. I mean, you can be fancy. And then I create an attack that is gonna use this and inject sections inside my ransomware. So again, this is the same boilerplate as before when I add, again, my Petya ransomware and the Satan ransomware, the Satan malware. This is exactly the code I showed you before. So now this attack uses genetic algorithms and for example, is gonna, add things until the evasion is done, or either until the number of queries is reached. And this basically is like the physical demonstration of what I told you before. And when it's gonna stop running, and if like there are no other surprises, Malcolm Malcolm is like, is like breaking a castle, is a sand castle. So as you can see here, so the first sample, that is Petia, starts from 91, and then it decreases over time until 0.0099. And 0.0099, it means that is the 0.9% of probability of being malware. 0.9. And the other guy from 1%, from 100% goes to 0.04, which is 4% probability of being a malware. So this just by combining section extracted from goodware programs, and it works. So from my point of view, it's nice because I'm the guy with the red, with the black hat, and I like to break things. But it means that this technology is super fragile from this point of view. So again, if you take this guy and you save it, and then you open it again. So now it's the adv.exe. You can see that it's still a problem. And just to let you know, let's just take this file and see what VirusTotal think about it. So VirusTotal is that online service that takes in input a file and it's gonna score it for you. So let me see. Sorry. So this was the 0. So it should be. I'm gonna use both of them just to to show you. Let me take a sample. So I'm gonna take like the Petia file and I'm gonna upload it to VirusTotal. As you can see, the Petia ransomware, is still as ransomware by all of these guys. Okay, and then there are some of them that, we just don't care about them. But as you can see, like a lot of them see it as a real malware. And now I'm gonna do the same with the Satan malware. Come on. Okay, anyway. Let me, I hate when this web application doesn't work as, thank you. Okay, as you can see again, and this, everybody see that this is malware, right? Okay, so remember this, this 60 or 557, and now I'm gonna take like where is it? The one that I created. So this is the malware that I created before with attack, adv.exe, and I'm gonna push it on VirusTotal. So since this is a new malware and it's not been analyzed by anybody, I'm gonna let it analyze for me. So of course it's still a malware, so some are gonna still detect it. But it might be also the case that from 60, maybe we are able to evade a bit more of them. Come on, you can do it. I'm confident you can do it. Come on. So, okay, remember that number before was 60, just to mention. So it means that here, some of these guys, oh gosh, really? Okay. some of these guys were, I was able to lower their score. That's, I won't comment much of that, but that it's, it's kind of creepy to my point of view, because it means that some vendors might be vulnerable to this thing. And lastly, what I would like to say is that, and now I know that everything is gonna fall apart, but I'll still try. So this new xc.file was the ransomware that I created, and I'm gonna try to import it inside my VM. So can you see my malware lab? I think yes. I'll now drag and drop it. So of course I had to disable the Windows Defender, of course. But so okay, yes. So as you can see here, let me. Where's the magnifier? Okay. So as you can see here, what can you see from this? Let's try to guess. So this is the adversarial
file. It's an executable file with an icon of a PDF.
Exactly. And what else? So for those who are not familiar, this shield here means that this guy needs privilege. So it's a program that is gonna use some restricted APIs, and it's gonna ask me. I hate the magnifier. Okay, if I double click on, what happens? Yeah, I don't care. If I double click on this, it's gonna, hey, please give me your admin. I can try to. Don't worry, I totally feel you. I mistype a lot, and yes, it asks for administrator privilege. So first of all, I'm gonna do that later, but why I'm so happy about it? Because I perturb this by adding sections, and the file is still executable. How I know that? First of all, if the icon is not corrupted, because sometimes if you mess with the file, you end up with something like this. That Windows doesn't know anymore how to parse, and the icon is totally broken. And that's the first red flag. Second good thing is that it recognizes that it means it has the metadata in the correct way, because there is this badge. Of course, not all malware, but this particular malware requires the privilege. And if I see already this, I'm happy, because it means that I didn't break the format. So then if I click on it again, this is asking me if, asking for user control. So it means that the loader was able to load it. And then just for, let me see if I remove the connection from the VM, because this is a ransomware. I don't want to destroy also my machine. So connection is absent. Okay. So we are all in this together. Let's see what happens. So I executed it. And as you can see, nothing happened. Why? Let me open Task Manager. And just to see performance. It seems that, oops, something really happened here. So the ransomware literally caused me a blue screen of that. So let me just try to reboot the virtual machine. You can, come on guys, okay. So, let's see what happened. It's a ransomware. So basically it ciphered everything. It can't find Windows anymore, because it also, how can I say that better? It cipher, it really damaged my computer. So it's not, my virtual machine is not even working anymore, because it can't find the operating system. So that was an adversarial malware, because I tampered with it, and let me take, let me restore a snapshot. Okay, just because I need this virtual machine. But the point is, I destroyed that guy with an adversarial malware. It was working, so the practical manipulations works. So I think that, I would just give you some more pointers. So if you want to use second-hand malware, you just go to GitHub and try second-hand malware. If you want to use like a command line tool, you can go to this Strike, and basically I'm gonna okay, come on, I'm gonna give you like a very, very small example about it. Okay, full hacking more right now. So so basically this tool is second-hand malware, but from the command line. I'm not gonna do like all of the things just because like I think it's tedious, but it's nice to see at least one of it. And okay, so basically I have commands. So I want like my target is malconf, and I said it. Then I want like some data, and let me see. Oh, again, sorry. Let me put this into the monitor and let me. Okay, data model sample. Okay. So there is the data command that it asks me for like a folder, and then I'm gonna pass this. So now I have like this is loaded, and I can. So this is basically the network, and this is like the data, and I can use like the predict function, and it's gonna score it for me. So basically, I'm doing the same thing I did on in the notebook, but on the shell. Oh no, I reset everything. I'm sorry. So data, target. Okay. Now I want to set the attack. So the attack can be set with this. Let's do the white box because I'm lazy. The white box command, and the white box command is telling me that I have to like choose an attack from this list. So it's white box. Okay, white box minus type is, let me say, partial DOS, and let me just 10 iterations, and it's fine. Okay, then I can just hit run, and Strike is gonna basically do everything that I had to code, just in this interactive way. I just said like 10 iterations are like super few. Okay, and ta-da! So this is how you create adversarial malware, also by typing commands in the shell. So for the one who are familiar, this tool is inspired by Metasploit. If someone knows Metasploit, please let me know, because it's just a nice thing to know. Metasploit is a thing you can use for crafting exploits toward like normal software in this way. So in a very, very interactive way. So this concludes the lectures, and I hope it was interesting for you. And I'm gonna leave some minutes here for the questions, curiosities. Even if you, hey, I'm interested in that. Can you give me pointers or whatsoever? Let me also give you my. If you need to write some, if you need questions or whatever, you can find me here. Let me just share my machine on again. Okay.
Luca,
so,
I have a question.
Tell me, yeah, I'm here.
Maybe I am lost during the discussion. I don't understand the meaning of the confidence that you get after that you apply the patch.
Sorry. Okay.
Because after that you applied it and we have a confidential level very low, if we put this malware on the web, we still receive a lot of feedback that is still a malware. So which is the meaning of this confidence level?
Okay, so what I showed you was a transfer attack. So the confidence is the confidence of the network that I use for computing the attack. So it's the surrogate model. Then I optimize the manipulation on the surrogate, and the surrogate is evaded. Then what I did is that I take it and I try a transfer attack. So as I told you today, transfer might not work, but it worked for a few of them, because if you remember, the first analysis said that 60 over 66 said that that was malware, and after the adversarial manipulation, 50 over 66 said that that was malware. It means that 10 guys over there were evaded by the adversarial attack. Hence, the transfer attack worked for at least some of them. So the confidence that you saw here was like a number from 0 to 1. That is the probability of that model to see. Sorry, it was the probability.
Okay, yes, it's clear. It's the confidence of the surrogate model.
Exactly.
Okay, it's okay.
But then the scary thing is that, of course, to conclude the answer of the question, you might say, okay, but you told us like a lot of nice things, and then you're not evading virus total. Consider that on virus total there are not only machine learning techniques, but also signature-based detectors. And by signature-based means that if there is this string, this is malicious. It's not even machine learning, first of all. Second thing is that the surrogate that I used, so the attack that I used, so the only 58-byte manipulation, is very, very weak. And just to comment on it, let me open like one paper. Okay, so that attack is very, very poor because it edits like few bytes, and on top of that, malconf is a very, very bad classifier. So if you want to do something better, you should use like an attack like section injection. Come on. You can do an attack like section injection with the addition of benign content, and this is what happens. So I had anonymized the name of the vendors, but this is the original detection rate, and this is after. So again, here the surrogate was a very, very robust classifier that was a decision tree classifier, and the attacker was stronger. So, and these 9 guys are 9 commercial products that are basically have been labeled as top vendors. And of course, I had to anonymize them. And with one of them, I also have like, a processing mean, like I send them an email saying, guys, I broke your models. And they say, oh gosh. And I'm still waiting for them to patch that. So I'm under NDA right now for that. But this was kind of one of the hugest one, but I can't tell you which one because I'm under NDA. It's not something that I'm making up. It really seems like, yeah, believe me, it's true. It's true. It's just that I don't want to be, to be chased by companies, because in one of my science paper, I put like their names here because it's also not ethical. So, but yes, to answer the second part of your question, of course, not all of the attacks transfer in the same way as the other, but there are some that do transfer. Did I answer the question?
Yes, thank you. I want to point out one thing, because in the past I injected stuff in other program. I injected the malware in some program, and I saw that modifying a couple of lines the detection of the antivirus decrease a lot.
Yes. Yes. Mm-hmm.
So my question now is the following.
Mm-hmm.
Except for signature-based antivirus,
yes,
how antivirus can protect our system? Because I mean,
okay.
now we know that there is a problem of there are a lot of malware that born every day. I
Yes.
don't know, maybe some hundred of thousand malware each day. So how can protect us using machine learning? Does exist some countermeasure for this or not?
So the question is totally interesting, and I want to, where is the, oh gosh, I can't find it. So yeah, basically Windows malware is like 1 million samples are uploaded each, I don't remember if week or month, but it's huge. And the problem with antiviruses is that the only thing that really works is signature based, because so you observe a threat and then you study the threat and you say, okay, this is working because there is this, this, and that. From the machine learning perspective, people are using these tools like either completely, in a completely data-driven way. So there are a few companies that do that, or either by using both of them, like in an adjacent way. The one that uses also only machine learning, are to some extent more robust and more vulnerable with respect to signature base at the same time. More robust because they generalize. So you don't need to create a signature for each malware, but you can, the learning model generalize over the space of malware. And even if a variant came up, you don't need the signature because it's kindly similar to the one you already saw. But on the other side, it's much more vulnerable because it's statistics. And with the things that I told you, you can bend statistics to your side. So the state of the art right now is that companies are using them mixed in a hybrid way, but they are using the model like they're not deploying the model inside your device. It's more like you send them. I take like the sample inside my operating system, and there is like an engine that sends it to the real model online. On top of that, this is not entirely true, because if you study a bit more like Windows Defender, you understand that there is a local model stored inside your machine somewhere, because it's not only working with with signatures. And this is done also by other vendors, and is something like it could be like a cool project to like maybe more industry speaking than research, understanding how to take these models, reverse them, and use them as a surrogate to attack all of the others. So I think I replied to one part of the questions, right? Right?
Yes, okay.
And the fact for the manipulation part, yes, when you alter 1 byte, you break all of the signature based. And this is exactly in this paper is basically stands for this random manipulation. Because you add something, you break the signature, which basically is sometimes is just the hash, and it's done. The problem is that from here to here, there is a gap. Like take these for instance. So 93% starting point, you break the hash, you go down to 85%, which is still okay. Then you do the adversarial attack and you go to 30%. So this is not signature. Because if it were signature, you would have seen here with the random manipulations. You get what I mean?
Yes.
So, that's a thing you usually do in this domain. You take the original detection rate, then you do something at random to discard all of the signature base, and then you do the real attack, and you see how these things go down.
Okay, I understand.
If you're interested in working with this, I have a lot of pointers of that. I mean, it's like I'm researching this by like at least 3 years by now. So if you're interested, like write me an email or like, you know, a message, and I'll be super happy, like, you know, to discuss it in many, many ways. Really.
Okay, I will do. I work as a cybersecurity analyst, so
You
okay.
know the
I will write an email.
yeah. I'll gladly waiting for that. Like I'm happy
Okay.
when, you know, there is this kind of, you know, joint things. So I'll wait for it.
Okay.
Let me just like, okay. So are there any other questions? So, okay, I think we are done. Thank you for, having listened to the lesson. Hope it was interesting for you. And if, like, you know, you go to sleep at some point at midnight, you came out with like a giant question. I mean, here there are like my addresses. You can either find me on Twitter or you can write me an email to this email account. I'm available. I mean, I'll be happy to answer all of your offline question. Now I'm gonna stop the recording. Okay.